SVP power when you attend to the grading over the RSVP task for the contrast. So, but despite this no change in SVP power, we thought we'd do the same analysis over our tuning functions. So this would be like an average tuning function over many trials. And so the center red kind of line here is the shown orientation, and it kind of falls off. And so then we look at the segments where there's a peak in alpha activity or a trough, as kind of organized by these 5 electrodes in the back. And what we see is not much difference when you attend to contrast. When you completely ignore the grading, we see an enhancement overall channels at the trough compared to the peak. And for when you're attending to the orientation of the grading, you see kind of this very specific enhancement near the shown orientation. Make this a little more clear. Here are differences of troughs minus peaks. So when you attend to the contrast, you see an increase in the shown orientation response at the peak compared to the trough. When you're completely ignoring it, you see this generalized increase of the channel responses when you at the troughs compared to the peaks. And then for the orientation, for the when you attend to the grading, specifically the counterclockwise shift that's about to happen with the grading, you kind of see this asymmetry here, where you see an enhancement at the troughs in the cued orientation. So for here on the right is always going to be the cued orientation. So this is reminiscent of the Naopakamanidi optimal strategy and orientation discriminations. And it seems like this optimal strategy may be also be following the alpha cycle. So as a quick summary of experiment 1, orientation and response profiles derived from EEG spatial patterns index attentional states, and the phase of intrinsic alpha oscillations modulates ignored stimuli in the deployment of attentional strategy, where the optimal gain pattern is at the trough of the alpha cycle. So now let's talk about spatial attention. So we asked the question, how is the sensory representation of space modulated by intrinsic oscillations? And so to do this, we also used a Ford encoding model, except this time we presented flickering checkerboards at various locations on the screen. And again, we're going to estimate the responsiveness of each electrode to these 36 different locations. And we do that with a basis set, kind of idealized receptive fields that are kind of a sharp Gaussian. Estimate our weight matrix, and then apply this to a novel spatial pattern of EEG. And what we get from this is a dynamic kind of representation of the stimulus range. So from an extremely sparse neural measure, we can reconstruct these very simple stimuli. So to study interactions with these oscillations, we had 2 different tasks. One, a training set. This is not behavioral training, but training for the model, where we presented 4 flickering gratings, and the location of these gratings changed from trial to trial. And then also an attention task, where from every trial, the same 4 locations were presented, 1 in each quadrant, and subjects were asked, were presented with a target that was a little dot, and asked whether it was blue or green. Importantly, for the attention task, subjects were either cued to the location of the target or were given a neutral cue. Right. So if we average across all of our subjects and all of our conditions, we can kind of see this little dynamic weave. And so for these 4 flickering stimuli, this is the power response. We used a wavelet to calculate power across time. And then these are our reconstructions. We can clearly see these 4 different stimuli that were presented to the subject. But one important feature is that the amplitude of these responses seem to be shifting. So we thought we'd kind of investigate that a little further. And we did that with the same sort of analysis that we did for the feature-based task. So we took the 5 electrodes in the posterior occipital region, and then found the peaks and the troughs. And if we just look at the neutral Q condition, then look at the channel responses, extracted from the peaks compared to the troughs, and then take a difference. Here we just see a kind of diagonal enhancement at the trough of alpha compared to the peaks. But since we are doing spatial attention, we thought we'd also look at the theta band. And so here we had a different region, these 5 electrodes here in the frontal. Again, the bandpass filtering 4 to 7 hertz compared to the peaks and troughs. And what we see here is a general enhancement when you're at the peak compared to the troughs. So putting this together, peaks minus troughs, theta and alpha. This would be the neutral Q, the location Q. These are our difference maps. And if we just inspect each quadrant, masking out the insignificant regions, then when you're given a neutral Q, 3 of the 4 quadrants are enhanced. There's more of a diffuse enhancement of the populations tuned to the different locations. And when you're giving a Q, there's a significant enhancement at the Q location. Okay. So to conclude, orientation response profiles and spatial reconstructions provide insight into the dynamics of feature and space-based attention. Intrinsic alpha oscillations modulate ignored stimuli and regulate the deployment of attentional strategy, where optimal enhancement is most apparent at the trough of the alpha cycle. And populations tuned to particular regions of space are regulated by the theta band with precise enhancement to the cued location of the visual field, or diffuse enhancement when no cue is given. Thank you.